This presentation is about a Theil-Index-based countermeasure against advanced vampire attack in the Internet of Things. Internet of Things and its applications are rapidly increasing, where several multi-scale sensors and devices are seamlessly blended. A major building block of IoT being IP version 6-based low-power and lossy networks, also known as LLNs, are leading to further development of IoT applications. However, due to their shared wireless medium, lack of resources, physical protection, and security requirements of RPL protocol, LLNs are particularly vulnerable to denial of service attacks. In this project, we propose a Theil-Index-based countermeasure to effectively detect and mitigate an advanced vampire attack. The motivation behind our project is the ongoing miniaturization of electronic devices and the maturation of wireless communication technologies, providing a solid foundation for the emergence and development of the Internet of Things, also known as IoT. The annual economic impact caused by IoT is to be in the range of $2.7 trillion and $6.2 trillion by 2025, according to the McKinsey Global Institute. These smart and connected devices can cater to a variety of civilian and military IoT applications, such as smart grids, smart transportation, smart cities, and smart homes. These technologies have to be protected at all costs because they would be integrated into our daily lives. About low power and lossy networks. LLNs have their own routing protocol called RPL, as LLNs are resource constrained and have limited processing power, memory, and energy. Also, the name lossy means that the links have low data rates and unstable connections. Another problem with LLNs is that their lack of physical protection, as nodes can be easily captured, tampered, or destroyed by an adversary, and due to the open nature of the wireless communication, an adversary can overhear, duplicate, corrupt, or even alter sensory data. About advanced vampire attacks, which I will also refer to as AVAs. A malicious node manipulates the source route header of received packets, then generates and sends the invalid packet with a fictitious route to legitimate nodes. Where an adversary only amplifies the cumulative network energy consumption, the AVA can disrupt immediate service availability as well as permanently disable the entire network. At a glance, an AVA on LLNs results in excessive energy usage for the entire network, as a large number of manipulated data packets with a fictitious destination MAC address can cause intermediate nodes to reply of massive error messages. Each intermediate node has to receive and forward more and more error messages, which result in significant energy consumption straining the LLN nodes. This mass error messages from the legitimate nodes can cause a denial of service in LLNs. The figure on the right is an example of an AWL happening on an LLN, where the LLN border router is a DODAC route that sent a message to N2 to deliver on the downward path, yet an adversary has compromised N2. Thus, the subsequent nodes in the downward path will send an error message to each other upwards to the DODAC route. Theil-Index-based detection. Our countermeasure is designed based on the Theil-Index theory. Some background on the Theil-Index theory is that the formula is typically used for finding economic inequality. In particular, if the samples are evenly distributed, a higher Theil-Index value can be observed, such that it is closer to 1. Meanwhile, if lower Theil-Index value means that the samples are not evenly distributed among classes, where the Theil-Index value is closer to -1. In our context, we apply the Theil-Index value to the MAC address space. If an AVA is happening in a random fashion, the Theil-Index value is closer to 1, and if the MAC address space is clustered, then it is closer to 0, as we cannot have a negative MAC address space. As each intermediate node records the destination MAC address of the received data packet within a specific window, then once the advanced vampire attack is detected, the attack mitigation procedure is triggered at the intermediate node, who is the next hop for the suspected adversary, to eliminate the attack by reducing the number of accepted data packets from the adversary. Our process was to first check articles relating to our specific attack on LLNs, where we found none at the time. Thus, we looked at other similar attacks on networks similar to LLNs. We settled on using the Theil-Index theory, as the TT value is the same as redundancy in information theory, which is the max possible entropy minus the observed entropy. There were 3 versions that we could choose from. However, we chose the first one as the other 2 were more complex than our needs. For our project, the Theil-Index is equal to the summation of the MAC address space equally divided into M groups. S subscript I is the share of the destination MAC address of group I. The Theil-Index value of group I is equal to the destination MAC address of the JS packet in group I, plus the summation of all the groups multiplied by log of the average destination MAC address of the group divided by the average value of all MAC addresses of all groups. Lastly, I simulated a random fashion AVA attack in Java, which my partner helped me optimize the division of the groups. After, our mentor took our code and applied it to Omnet++, which is a software that can simulate various networks to run it against the other two countermeasures of similar attack scenarios and the non-attack state of the network. In our performance evaluation against two other approaches of similar attacks, respectively, a route examination-based approach and a forwarding-based approach, we see that our countermeasure gets a better detection rate as the attack traffic increases while also consuming more cumulative energy on the network. However, it consumes less energy than the other approaches while having a better detection rate of an AVA. In the figure on the left, the detection rate is measured by window size, and we observe more tampered data packets received in a larger window lead to more attacks detected due to a significant increase to the Theil-Index value. Also observed in the right figure, as the window size increases, so does the energy consumption slowly, as the number of accepted tampered data packets from the adversary significantly reduce in the next window. If you would like to read more about our project, it is published on IEEE Explore, and the two approaches we ran our countermeasure against are also there. Thanks for listening and considering our project.